In the eloquent words of Stan Gâteaux, the essence of mathematics is not to make simple things complicated, but to make complicated things simple. Welcome, fellow mathematicians, to Math Explore Infinity, where the wisdom of Stan Gâteaux resonates. In today's lecture, by the way, Stan Gâteaux was actually a brilliant American mathematician, right? So in today's lecture, we are going to immerse ourselves into optimality in constraint problems, right? If you're on the quest for, before we start, if you're on the quest for a smoother understanding of mathematics or an end for support in your studies, then you are found the right place. You're in the right place, right? And also, I would say that, if you ever wish to improve your mathematical knowledge, then I would say that being part of our mathematical community is a must. So I extend a warm invitation for you to subscribe to the channel. Of course, the choice is yours, right? And you have the right not to subscribe as well, but who would want to miss out on simplifying the complexities of mathematics? Well, I don't know. Okay, so let's get into business. So far, we were able to derive an analog of the Fermat principle for functions that exhibit non-differentiability at certain points, right? And we also established some calculus rules, right, for subdifferentials. And today's lecture is about combining our Fermat's principle for non-smooth functions, right, with the sum rule in order to characterize minimizers of convex functionals under constraint. Okay, so in continuation with our previous lecture, right, our main result is actually entailed in Corollary 4.10. So this is so let U right be a subset of Banach space X, right, be non-empty, convex and closed. Right, and let f, right, capital F, be a function defined from X into the completion of R, be proper, convex, and lower semicontinuous. Lower semicontinuous. Okay, so let me just highlight assumptions that we have on F: properness, convexity, and lower semicontinuity. And we need our set U to be non-empty, convex, and closed. Okay, now if furthermore, so if there exists, if probably I put it in color, right? So if there exists a point x0, right, in the interior of U intersected with the effective domain of our functional f, then put it here, then x bar, a point x bar is an x bar in U, right, is a minimizer of f, or just say x bar in U solves mean of f of x, right, over x in U. And this is another way of saying that x bar is a minimizer of f, right? So probably I put it here. So this means that probably I use this color. F of x bar is the mean f of x over x in U. So then this holds if and only if, so x bar is a minimizer if and only if of this problem, if and only if there exists a linear bounded operator that we call 𝛏. And this is not well written. Yeah, 𝛏 in the dual space, right? Such that 𝛏 always find it difficult to write this Greek letter, but that's okay. If only if there exists a linear bounded operator such that 𝛏 is actually in the convex subdifferential of f at the point x bar, and we also have that the duality pairing of 𝛏 applied to 𝑥ₘᵢ minus x, right? This is the duality pairing. This is actually greater or equal than 0 for every 𝑥ₘᵢ in U. So okay, so if you have just kind of a quick recap, the summary. So if you want to solve this problem, right, then the point x bar, right, is a minimizer of this functional f if and only if you can find a linear bounded operator 𝛏 in the dual space, right, such that 𝛏 is actually in the convex subdifferential of the function f at x bar, and this inequality here holds, right? I mean, if you pay attention, then you will see that this is another way of saying that minus 𝛏 is actually in the, in the normal cone. Okay, so let's go into the proof. Okay, the first thing is actually, again, we make an observation. Observe that minimizing the function f of x, right, over x in U, right, is the same as minimizing the extended functional, the extended functional f of x plus delta U of x, right, over x in x, right. So for this, we define the extended functional to be j. So put j to be f plus delta U, right? This function, this is our extended functional. Now, due to the assumptions that we have on f and u, so due to the assumptions on our function f and u, right, we can conclude that our extended functional j is convex, right, as sum of two convex functions. It's convex proper, and lower semicontinuous. Right? I mean, LSC stands for lower semicontinuity, right? So moreover, by the Fermat principle, and this was actually theorem 4.3. Anyway, I think I have a lecture only on the Fermat principle that I strongly invite you to have a look at. Check it out, right? So moreover, by the Fermat principle, so this is theorem 4.3, right? We put the link at the upper right corner, so don't worry. We have that, x bar is a minimizer. F of x bar is equal to the minimum of f of x, right, over x in U, right, which is again the minimum of our extended functional, right, over x in x. So by Fermat principle, we know that this is equivalent to, I'm just writing this way, right? This is equivalent to saying that 0 is actually in the convex subdifferential of j at the point x bar, right? But the convex subdifferential of j, this is again the convex subdifferential of f plus delta u, right, at the point x bar. Okay, but now remember we had the assumption that x0, since there exists x0, right, in the interior of u, right, which is again, the interior of the domain of delta u, right? We know by theorem 4.8, we know by the sum rule, right? We saw that, that the sum of convex subdifferential is not always equal to the sum of, let me just probably write it down. So we know by theorem 4.8, right? This was actually the sum rule, right? The sum rule in the lecture on subdifferential calculus. So we know by the sum rule that the convex subdifferential of the sum of two functional f plus delta u, right, at the point x bar, we know that this is equal to the sum of the convex subdifferentials, right? This is equal to the convex subdifferential of f at the point x bar, right, plus the convex subdifferential of delta u at the point x bar, right? So this equality here follows from the fact that that x0 is in u0. It's actually in the interior of the set u intersected with the domain of f. So this was actually the condition for us to have this equality here. So because of this, there's f of x bar, right, is equal to the mean f of x over x in u, right? This is equivalent to saying that 0 is actually the convex differential of j at the point x bar. But we saw that the convex differential of j at the point x bar is again the sum of the convex differential, right? So we just write 0 belongs to, just put we just write it this way, right? Convex differential of f at x bar plus convex differential of delta u at x bar. So probably let me just try to create some space. Okay, so this is this. Okay, now as I said already, so don't get confused. This is again, so everything's fine. So now this is equivalent to saying that this is now basically we are just applying the definition. So this means saying that 0 is actually in the convex differential, the convex differential of f plus the convex differential of delta u at the point x bar. So this means that there exists, this is by definition, purely by definition, there exists xi, right, in the convex differential of f at the point x bar, right, such that minus xi is actually in the convex differential of u, of delta u, right, at the point x bar. And now this is equivalent to saying that this is by characterization, right, of we saw that this was actually the normal cone, right? So by characterization of this, the convex differential of the indicator function, we have that this is equivalent to saying that there exists xi in x star, right, such that xi is actually the convex differential of f at x bar. And this duality pairing, saying that minus xi is in the convex differential, means that minus xi at the point x tilde the minus x, right? And this is the duality pairing. This is actually less or equal than 0, right? For every x tilde in u, right? But I can even multiply by minus and changes the the sense of the inequality, right? So I can basically remove this and then just put this, right? So this whole, of course, for every x tilde. Again, as I said, so this is by characterization. characterization of subdifferential. 𝑥ₘᵢ of x bar, right, as normal cone. Okay, so this basically proves our result, right? So this is the end of the proof. And it looks ugly. Okay, so of course, I mean, this is the end of the proof, but let me draw your attention on something. For those who are familiar with nonlinear optimization, let me just look for a very nice color. Yeah, probably this one. So observe that this condition here, I mean, observe that this condition here actually coincide. This coincide. Oops. This coincide with the classical 𝑥ₘᵢ, right? Just like Karush, Kuhn, Tucker, Karush. Karush, Kuhn, Tucker condition. Right? I mean, of course, this is in the case if f, right, is Gâteaux differentiable. Right, so this condition here, I mean, if our functional f is Gâteaux differentiable, then we saw that the convex subdifferential of f is, I mean, is the singleton Gâteaux derivative of the functional f, right? So this actually coincides with the 𝑥ₘᵢ conditions, right? I mean, if you're familiar with with nonlinear optimization. Okay, and of course, also another point is that let me just say, yeah, here, yeah, the existence of I mean, of an interior point x0, right, is an analog of the Slater condition, right, that we usually need to prove the existence of the Lagrange multiplier, right, xi for the inequality constraint. Yeah, so you see that, I mean, everything, I mean, things are kind of consistent, right, with what we know from nonlinear optimization. Okay, yeah, so this is basically all I wanted to share with you today, right? Thank you for following along. Of course, if you are not yet part of our mathematical community, feel free to subscribe, right, and secure your spot. Otherwise, keep watching from the window, right? I mean, the choice is yours, right? Until next time, keep improving your mathematical knowledge and happy learning.